All right, for the first ones, we are looking for the direction of the magnetic force on each of these situations. Right here, we have two directions, obviously. One is to the right and one is up. The thing that is to the right is the charge is moving to the right, so that would be represented by your thumb. This in the background here, in the background of all of these, is the magnetic field B, so that would be my fingers that are pointing up. And then I'm looking for what my palm is doing. Actually looking for what my palm is doing for all of these. The next one, so you could say your fingers are going to the right and then your thumb should be pointing to the left. This one, circles, that would be your fingers, and circle means out of the page. Your fingers should be pointing out, and up is the charge, so that should be your thumb pointing up. Here, your fingers are the magnetic field in the background that's going into the page, and then to the right would be the charge, so that is your thumb to the right. And the last one, your velocity, is your thumb that is pointing out, so your thumb would be pointing out, and your B field, which is represented, your magnetic field is represented by your fingers, those would be down the page. And again, we're looking for our palm on each of these. So these all are either positive or don't say a charge, so those would all use my right hand, but this one is negative, so I should use my left hand because it is negative. Also with these, we either have a 50-50 shot, so this one, because we already have right and up, it's either in or out. This one we've got right, left, we'll get to that in a second. This one, our fingers are out and our thumb is up, so the only thing left is right or left. Here we've got into and right, so the only thing left is either up or down. Here we have out and down, so the thing left is left or right. Alright, so the first one, we have our left hand because it's negative, our fingers are pointing up, our thumb is pointing to the left, that leaves our palm, or our force pointing into. Here, if you try and make your fingers go to the right and then your thumb go to the left, it just doesn't work. This one is impossible. Here, our fingers are pointing out like this, but then our thumb is pointing up, so fingers out, thumb up, that leaves my palm facing to the right. Here, into, fingers into, thumb to the left, that leaves my palm facing down. Here, my thumb is pointing out, my fingers are pointing down like this, so that leaves my palm facing to the right. Number 2, an electron is moving into the page between these two magnets. What is the direction of the force? So I'm looking for my palm. My electron is moving into the page, so that would be your thumb that's pointing into the page. And be careful, it's electron, which means use your left hand. And then we need to know what our fingers are doing. Our fingers are the magnetic field, and magnetic field points out of north and into south. So see how our magnetic field or our fingers would be pointing to the right. So I'm going to have my fingers pointing to the right, left hand, because it's negative. So fingers pointing to the right, and then my thumb pointing into, that leaves my palm facing up the page. So here your force was up, and it was either up or down, so we already had right and into. Number 3, sketching the magnetic fields around each of the currents below. So this is going to be our second right hand roll because we're looking for field and we know the current, your thumb. So this one would be thumb down, looking for what our fingers are doing. Here, thumb to the right, what are our fingers wrapping around, thumb into, what are our fingers doing. So the first one, use my thumbs up rule. So my thumb is going to point down. That's going to make a circle around like this, which means my fingers are going to be coming out on this side and they're going into the page on this side. So it would look like this. The next one, thumb to the right, my fingers are going into the page here, and then like if you imagine this is the wire, they're coming out on the other side like this. This would be X's. Or if you're very artistic, show it coming around like this and going in. I'm not very artistic, so it doesn't really work, but same idea here. It comes out of this side and around and in like that. And then the last one, your X is your current, your thumb is pointing into, and then your fingers are going to curl around like this. So you're going to curl around, in a clockwise direction. Number 4, direction of the magnetic field inside the coil and label the north and south pole. So first, let's just draw the direction of the current in the front is down. It's going up in the back, but I just want to look at what it's doing in the front. So my thumb is pointing down like this. Whatever side my fingers are pointing into, that would be my south pole. So they're pointing in here, that's my south pole, this is my north pole. And then the direction of the magnetic field will be just that my fingers are going in this side, and then they're like coming out this way. So that's the direction of the magnetic field inside the coil. On the outside, like this compass, so it's going to come out of north, it'll go back into south, which means it has to turn around and like go around back this way, so this should be pointing to the left. Number 5, direction of the magnetic field in the center. So this is positive going to negative, so that means the current is going to go around like this, because it is going from the positive around to the negative side. Now, current is your thumb. You can't really do your thumb in a circle, so let's just break it up into the parts. So if I have my thumb like this, it's going in right here and it's coming out of the page in the middle. If I look at this piece right here, I have thumb this way, fingers going in on this side and they're coming out on this side. And then lastly, thumb down, they're going in on this side and then coming out on the other side. So the direction of the magnetic field in the center of the loop is out of the page. Number 6, wire is being pushed into the page. What is the direction of the induced current? So I'm looking for what my thumb is doing. My fingers are going out of north and into south, so my fingers should be going to the left. And then it was pushed into the page. Well, if it's being pushed into the page, I'm going to feel an opposite force. So I'm going to feel force out of the page. So my palm should be facing out of the page. Fingers this way to the left, palm facing out. That leaves my thumb or my induced current pointing up. So your answer was it goes up the wire. And just looking at the wire is either up the wire or down the wire. If you're like, wait, but I thought this is supposed to be opposite because it says induced current. That's true, it's the opposite force. I said it was being pushed into the page, so my palm would be out. So I already did the opposite force. So whatever I get for my current is the direction of the induced current. Number 7, determine the direction of the magnetic field for a negatively charged particle that moves to the right and has a force down. So moving to the right would be my thumb is going to the right. A force down, that's palm would be down, and I need to be careful because it's negative, so I use my left hand. So just because this is right and down, I know the only thing left is in or out, so I can cross these ones off. Now I'm going to make my thumb go to the right, I'm going to make my palm face down the page like this. It's easier to see at the front. So thumb to the right, palm down, that means my fingers are pointing into the page. So your answer is into the page. 8, we're trying to find the direction of the magnetic force on the electron, so again, use left hand. Here my thumb is going to the right, and my fingers are pointing into the page, and we're looking for what our palm is doing. So fingers in, thumb to the right, that leaves my palm facing down the page, like this. So, down. Number 9, so a proton feels a force out of the page, so that's palm would be out of the page. Which way is the proton moving? So I'm looking for what my thumb is doing. My fingers are going out of north and into south, so that means my fingers are going to the left. So fingers to the left. It's a proton, so I use my right hand. Fingers to the left, my palm is facing out. Okay, that fell down. Yeah, okay. Fingers to the left like this, palm facing out, that leaves my thumb pointing up. So the proton must have been moving up the page. The north and south pole of the electromagnet. So let's first determine what is the direction of the current on the front. So this is going up, but that's in the back. It turns around and comes down in the front. This is the current in the wire. Current is represented by our thumb, so that would be my thumb pointing down. Whichever side your fingers are going into, that is your south pole, because the field points out of north and into south. So thumb down, they're going in on this side, so this is my south pole and this is my north pole. Here, the current is going up in the front, and then it's going down in the back, so I'm going to have my thumb pointing up in the front. My fingers are going in on this side right here, so then this is my south pole and this is my north pole. Here, I have to draw in the current. It goes from the positive, like this, so that means it's going up in the front, and then turns around and goes down in the back to get to the negative. So thumb up in the front, it's again fingers scooping in on this side, so that's my south and left on the north. 11, given that the particle entering the magnetic field as shown feels a force down, so that would be palm down. And the direction it's moving is to the right, so that would be my thumb to the right. And my fingers are going into the page. Is the particle positive or negative? Just asking, does it work for my right hand or my left hand? So I'm going to go fingers in, thumb to the right. That would leave my force for my palm facing up. Incorrect. Let's try it the left. Fingers in, thumb to the left. That leaves my palm facing down. That agrees. So because it works with my left hand, that means that the particle must be negative. So works for left hand. Your left hand is specifically for negative particles. Oh crap, that was for up here. My bad. Number 12, again asking if the magnetic force is down, so if that is palm down, and I do have my thumb going to the right here, but circles in the background means my fingers are pointing out of the page, and I'm again looking for positive or negative, so right hand or left hand. So I'm going to have my fingers pointing out, thumb to the right. See how my forces would be pointing down? That works for my right hand, so that means that this one is positive. Apologies, the negative was for the above one right here. Direction of the force, the electron would feel entering these magnets, so this would be thumb to the left. My fingers would go out of north into south, and those are my fingers, not the force, because it's a magnetic field that points out of north into south. And we're looking for the force, or what my palm is doing. It's negative, so I'm going to use my left hand, fingers pointing up, thumb to the left, that leaves my palm facing into the page. It was either into or out of, because we had left and up. Number 14, an electron in a magnetic field directed down, so that would be fingers, because our field is our fingers down. Force to the left, that is your palm that's facing left. The electron, so that whatever way the electron is moving, I'm looking for what my thumb is doing. This is electron, so that'll be negative. Fingers down like this, palm facing the left, that leaves my thumb pointing out of the page. An electron is coming out of the page straight at you, so that would be your thumb pointing out. Magnetic field is switched on and deflects the electron to the right. So that means your force, deflect is, it feels a force to the right. So then that means that your palm would be to the right. And we're looking for the direction of the magnetic field, so you're looking for what your fingers are doing. Again, this is electron, so use your left hand. So I'm going to make my palm face the right, thumb out, that leaves my fingers pointing up. And it was either up or down because they have to all be perpendicular. Proton moving to the left, so that is thumb to the left, and force up, that is palm up the page. Direction of magnetic field, that is your fingers. Proton is positive, so I'm going to use my right hand. Thumb to the left, my palm needs to be facing up, so that leaves my fingers pointing out, and it was either in or out. But I get up. The wire loop shown has electron current, that means use the left hand. What is the direction of the magnetic field at point P? So this is again asking what is the direction of the magnetic field in the center. So I'm going to use this right hand rule because I'm talking about magnetic field caused by a current, so fingers wrapped around my thumb. So right at this point, if this is like the wire right here, my fingers would be going in here, they'd be coming out in the center. But like it would be facing down here, they'd be going in on this side, coming out on this side. Here, following the circle, it would be pointing to the left, so it would be going in here and coming out on the center point. So at point P, your fingers are pointing out of the page. Current carrying wire located in the magnetic field. The wire is pulled out of the page. What is the direction of induced current? So induced current means opposite force. So whatever way it was being pulled, it will feel a force opposite that. So this one, the wire is pulled out of the page, so we're going to have a palm or a force into the page. And then, of course, our magnetic field is pointing up, so that would be our fingers pointing up, and we are looking for the direction of the current. We're looking for the direction of our thumb. It doesn't say anything about negative, so we use our right hand. So palm facing into, thumb or fingers pointing up, that leaves my thumb pointing to the left. And it was either, just looking at the wire, it was either going, the current's either going to the left or the right of the wire. So we found that it was left. Which side in transformer always has the more number of turns? the one that has the highest voltage. So if you look at your NP over NS equals VP over VS equals IS over IP. So these two do the same thing. If the primary has more number of coils, then the primary will also have more voltage. Sometimes the secondary has more number of coils. That means it would have more voltage. So it's not primary or secondary unless I know it is a step up or step down transformer. In a step up, then the secondary side has more turns. In a step down, then the secondary side has less turns. But I do know more turns always goes with more voltage. Secondary current in a step down transformer. So here, this is a step down transformer, which means the number of coils decrease, which means your voltage decrease. But then I does the opposite thing. Your I is going to increase. So the secondary side will have more current. Transformer has an input voltage, so I'm going to call that the primary voltage and the primary current. Secondary has, this is number of coils, that's secondary number of coils, and this is amps, that's secondary current. Should I talk about the secondary side? We want to look for NP. So because I have both I's and one N, and I'm looking for another N, I'm just going to use the NP over NS equals IS over IP. Remember, we have these like three ratios. These three ratios, but you never need to use like 3 at a time. You're just comparing 2 at a time. In this case, I'm going to cover this up and compare these two to each other because I have both of these and I want an N. So now we're just plugging in. NP is what I'm looking for. NS was 5,000 equals IS 1.5 over IP, which is 30. And now we cross multiply, so that's going to give me 30 NP equals, grab a calculator, 7,500, and then we just divide the 30 over, and that's going to give me my number of turns on the primary is 250. So if we look, it had 250 and now it has 5,000 on the secondary, so this is a step up transformer, and you might be like, wait, but the current got smaller. Remember, current does the opposite thing. For a step up transformer, you have more number of coils, you have more voltage, but you'll have less current. Now we're trying to find the secondary voltage, so I definitely need the VP over VS equation in my equation, but it doesn't matter if I use I or N. It doesn't matter at all. Let's use N, like NP over NS, and now it's just, okay, 250 over the NS, 5,000, equals VP, which is 220 over VS, and now we just cross multiply. So 5,000 times 220 divided by the 250, that's going to give me V secondary is 4,400 volts. And we know that the voltage would get bigger because our number of coils was getting bigger, so that makes sense at least. And lastly, our input power, I'm running out of room, so our input power is just the primary power. Power is IV. This has a current on the primary side of 30, and a voltage of the primary side is 220. So 30 times 220 gives me a power of 6,600 watts. You also could have found the primary or the secondary power because it's the same thing. You would have to use the voltage that you just got, the 4,400, times the secondary current 1.5, and you would still get the 66. Oh, you can't see that. That's okay. If you do the secondary current times secondary power, or sorry, secondary voltage, you still get the secondary power, and they're the same. So you still get 6,600. All right. Power supply that steps main voltage down from this voltage to this voltage. So obviously these are voltages measured in volts. If it goes from this to this is my primary, and secondary is what comes after. The primary coil has this many turns, and primary, what are the secondary number of turns? So I'm comparing voltages and number of coils, so NP over NS equals VP over VS. NP is 1,200 over NS, what we're looking for, equals VP, which is 240 over 6. So now we cross multiply, so 240 NS equals 1,200 times 6, which is 7,200, and we divide our 240 over, and that gives me the secondary number is 30. And then we always should check. This is a step down, so I should have less coils on the secondary. I started with 1,200, now I have 30, so it did get stepped down. Transformer has an input current, so that would be primary current, and an output current, secondary current. Which coil has more turns? Well, let's say the secondary coil, this has less current, this one has more current. Well, number of turns does the opposite thing if you look at our equation. Number of turns is P over S, whereas this one is S over P. So the one that has the most current will have the least number of turns and vice versa. I, or current, is that odd guy out here. So one with more turns, or the greater N, is the smaller current. So that would be secondary side. This one, if you're looking, you're like, oh, that's a step down. That's actually incorrect because that's the current is decreasing. The current is the odd guy out. Current decreasing actually means my voltage and my number of coils are increasing. So it would be a step up. How iron can become a magnet. The electrons spin in a unique direction. That's something we've talked about. 25, as shown in the diagram, a wire carries an electron current out, which of the following is the force point. So we've got a magnetic field pointing out of north and south, so that would be my fingers pointing to the right. Current would be my thumb, so my thumb is going to be pointing out, and I'm looking for what my force is doing. So my force is either going to be pointing up or down, my palm. So it's either P or R, so we can cross off these. My force isn't going to S or Q. So I'm going to have my fingers going to the right, I'm going to have my thumb pointing out, and that leaves my palm facing up the page, which is P. North and South Pole, so this is my positive, the longer end, and then this is my negative on this end, so it's going to go, current is going to flow from the positive to the negative, which leaves, if you're going around like this, your current is pointing down in the front, so make my thumb point down, whatever side my fingers go in on, that is the South Pole. And two ways to increase the strength. One, we could have more voltage or more batteries. The second is we could add more coils, like more turns or loops of wire. Here we are finding the direction of the induced current given which direction the magnet is pulled in. So let's start with this one. If it's being pulled to the right, that means I have a force to the left. My fingers are going into, and for all of these, I'm looking for what my thumb is doing, so I'm looking for current. Here, again, this is being pulled to the right, so my palm or my force is going to be to the left. My fingers are going to be pointing out of the page. This one, so this one isn't a first right-hand rule because I'm talking about poles. So if I pull a south pole away, if a south pole is being pulled away, that's going to try and attract back, which means a north pole is going to be created here and a south right here. And then here, if I push a north pole in, that's going to try and repel, which is going to create a north pole here and a south pole here. And now it's just going through and doing my hand rule to find the direction of the current. So the first one, fingers into, palm to the left. That leaves the current pointing up. Here, I have fingers pointing out, but then my palm needs to face the left, so that leaves my thumb pointing down. So this one was up, this one was down. Here, south pole, my fingers go in on south pole, thumb is pointing down right here. And then this one, south pole, fingers point in on, that leaves my thumb pointing up. So just to draw this in, my current would be pointing up on the front. Here the current would be pointing down on the front. Here we said the answer was down, down. And here our answer was up. Arranging so that they repel each other, which is the best arrangement. Well, like poles repel, so the same poles repel, so C is the only one that has same. These are opposite, they would attract. These are opposite, they'd attract. These are opposite, they'd attract. These would repel, because they're the same. 29, if the motion of the magnet induced is shown, which way was it moving? Well, if the current is pointing up, let's do thumb up, that would mean this is a south pole and this was a north pole. These two are going to repel each other, so the direction the thing was moving, if it was causing a pole that repels, means it must have been moving like into the coil. So you could say into the coil, or you could just say to the right. Either one of those, or just draw an arrow, I don't know. But if you are trying to push it into the coil, that will try to do the opposite thing, or repel, which would create a north pole there. Decrease the strength of the electromagnet, so I could decrease the voltage or decrease the number of wires, so use fewer wire coils around the nail. direction of electron current. So I'm again looking for thumb, and these right here would represent my fingers, but I have to be careful. Electron means use my left hand. So I'm going to have my left hand. My current is either going to be up or down the wire. If I have my fingers coming around to the right in the front and turning around like this, that leaves my thumb pointing down. So down is going to be from B to A. Here again, electrons moving from the left to the right, so you could say to the right, like this, and use your left hand. Or if you're like, wait, it goes from positive to negative, totally fine. If you're doing positive and negative, use your right hand then. I'm just going to say electrons moving to the left, that's thumb to the left using my left hand. My fingers would be going in on the top side and coming out of the page on the bottom, so that would be A. Given the direction of the field, determine the direction of the current. So I'm looking for what my thumb is going to be doing. Here, my fingers are going to the right in the front and to the left in the back, so I'll use my thumb pointing up. Here, my fingers are pointing up in the front and down in the back, so I'll use my thumb pointing to the left. Here, my fingers are going around like this, so that leaves my thumb pointing into. And then here, my fingers are going around like this, so that leaves my thumb pointing out. So to draw in the direction, that would be up like this. This one was to the left like this. This was into, and then this one was out. Magnetic fields around a bar magnet. So our rule is out of north and into south like this. And then, of course, it's going to go around like this. Anything that's showing out of north and into south would be a magnetic field running around the magnet. The direction of the magnetic field at point P, so current, that is my thumb. Now I can't make my thumb go in a square, so let's just start, okay, thumb up, my fingers would go in here and come out on the other side, so X, O's. Thumb this way, fingers in on this side, out in the center, like this. Thumb down, fingers go in on this side, they come out on the other side. And then fingers go in here and come out on the other side. So the direction of the magnetic field at point P is out of the page. Number 36 is a tricky one, so we want to find the force, so I'm looking for palm. Now you might say, well, your charge is going up, your current is also going up, and those are both thumb. I want the force on the charge, so I'm going to use the thumb is going up for the charge right here, and I need to know what is the magnetic field it's moving in. What are my fingers doing? Well, I have a current. A current creates a magnetic field, so see how I can use my second right hand rule to find out what the magnetic field created around the current is. So it would be out of the page on this side, and then now it's just a regular question. What is the force? So my fingers would be pointing out, my thumb would be pointing up like this. Oh, it's really hard to do that. So fingers out of the page, thumb to the up the page, that leaves my palm facing to the right. So the answer was to the right. So what we had to do here, just to talk through this again, so I need to know what the magnetic field direction that this charge is in. Well, I have a current. Current creates a magnetic field that's pointing out right here, so then I can ignore this and just say, okay, fingers out, thumb up. That one would feel a force to the right.